Okay, welcome back. This is 6.8, which is applications of logarithmic expressions. We find logarithms in a lot of calculations, a lot of physical phenomena. We're going to talk about a few of those things, and we're going to start with the magnitude of an earthquake. So the magnitude of an earthquake is given typically by an M, and these calculations can get a little bit complicated depending on where the earthquake is, the nature of the soil that it's in, things like that. But this is a pretty good baseline simplified equation to find the magnitude of an earthquake. So m is the magnitude, x is the function, and it is the movement in millimeters of the needle of a seismometer as long as that seismometer was 100 kilometers away from the earthquake when it happened, right? So there's a lot of ifs here, which is why it gets complicated, because if those things aren't met, this calculation doesn't exactly work. But, so I'll write this. X is the needle shake in millimeters. Okay. But this function is, the magnitude is given by simply a log of that x, the amount that thing shakes in millimeters, divided by 0.001. And magnitudes, if you know about earthquakes, you know a magnitude 3, not a big deal. Magnitude 4, not a whole lot of more of a big deal, but it's 10 times as strong as a 3. And then a 5 is 10 times as strong as a 4. And so on and so on. A 6 is 10 times as strong as a 5, and etc., etc. And that's because we're using a log base 10 here. So each one increase is a multiple of 10 in strength, in movement. So let's do a couple of problems. This is our equation that we're going to use. Let me get rid of it so I have a little bit of room here. But let's say we want to find the magnitude. We're going to find the magnitude of an earthquake for an earthquake that measures 200 millimeters. The little pen moved 200 millimeters on a seismometer 100 kilometers away from the earthquake. And that's it. That's all I really need is that x. So the m, x is 200, so this is the magnitude of a 200 millimeter shake, is equal to that x, which is 200, oh, excuse me, the log, I didn't write the log, the log of that 200, because that's my x, divided by 0.001. Right? So 200 divided by 0.001, you can think of this as also multiplying by 1,000, so this becomes log of 200,000. And if I throw this into a calculator, that log of 200,000, and again you can think about this before you throw it into a calculator. If this were 100,000, my answer would be 5, because it's 10 to the 5th, right? 10 to the 6th would be 1 million, so it should be 5 point something. Right? And so in fact, if we plug this into a calculator, I get and I round it to the nearest decimal place, because that's what they do when they report a Richter scale reading. They round it to the first decimal place, so in this case, we get a 5.3 magnitude earthquake. Let's look here. Alright. Now I want us to do the same thing in the next example when x is much larger. That's 20,000 millimeters. Right. That's a pretty big shake. So if I want to find this, the magnitude at 20,000 is equal to the log of that 20,000 divided by 0.001, which is to say that's the log of 20 million. Right? So it should be 7 point something. Right? There's 1, 2, 3, 4, 5, 6, 7 zeros. So 10 to the 7 is 10 million. 10 to the 8 is 100 million. So it should be closer to 7 than 8. But if I again plug this in there, I get that this is about a 7.3. Right? Which makes sense that it ends in a 0.3 because the other one was 20,000 or 200,000, I think, when I took the log of it. This is just 2 more zeros, so it's a 2 increase on the Richter scale. Okay. All right, let's suppose we have a 9.5 on the Richter scale magnitude earthquake. We want to go backwards and we want to find out how much shaking was happening on that needle in the seismometer. Right? So using this equation, that m of x equals the log of x over 0.001. I know my magnitude is 9.5, so I'll replace the m of x with 9.5. And now I want to solve for this x that's inside the log. Now to get that out of there, I'm going to rewrite this as an exponential. This log is a base 10, so it's 10 raised to the 9.5. Equals x over 0.001. Now, I could take 10, raise it to the 9.5 and get a really big ugly number, but I can also leave it and just multiply each side by 0.001 because this is 10 to the negative 3. I can write that instead of 0.001 as 10 to the negative 3. I've isolated my x on the right hand side. And I can take 10 to the 9.5 minus 3, so that's 10 to the 7.5. Right. I can plug that in, and when I get that, I get 3,162,278, rounded to the nearest whole number. Right. Which is a lot. If you look that up in millimeters, say most of us are Americans, that many millimeters converted to feet, it's a lot of feet. If you think about a building that's moving that much, that building's gone. It's not going to withstand this type of movement. Right? But that's how we would go backwards, and we found how much movement there is based on the magnitude of an earthquake. Okay. Let's move on. Let's talk about population. So, the first thing that we would have is that the population, like of animals or people or, you know, anything that grows, follows this. We have the population as a function of time is equal to, and a lot of times you'll see a p with a little o, and we call this either p naught or p sub 0, but it's the initial population or the population that when you started to observe. Multiplied by e raised to the r times t power. So that rt is in the exponent, it's the power, rate times time. Right? Now every growth model has some r associated with it, and for very simple unbounded growth, that r never changes. If you have things like limiting factors like limited space, limited food, things like that, then the r becomes not a constant. But we're going to deal with everything where r is constant, right? So let's take a look at this first example about alligators. We're given a growth rate. Alligators, they have a growth rate of 0.06, I think I saw. Yeah, and we want to find, let's see, there's initially 250 alligators in a swamp, and we want to find the population in 20 years. So that's the question, find the population in 20 years. Given the fact that we know our growth rate is 0.06, we know that there were 250 to start. So that 250 is this P naught. What I really want to find is P20. So the population 20 years from now is that 250 multiplied by e to that r, which is 0.06, multiplied by t, that's 20 years. And this is obviously a calculator question because E is that 2.7818 yada yada number. But you can make your life a little bit easier. I can write this as 250 e to the 0.6 times 20. That gives you 1.2. And if I multiply all of this out, 250 times e to the 1.2, throw it in your calculator, you should get somewhere around 830. So in 20 years, our population of alligators has gone from 250 to 830. Now, in this last example, our population growth rate was given to us, but it's not always the case. Sometimes we're just given 2 data points in time and we have to figure out what that rate is. So let's take a look at that. Our next example in the book, it just says a population grows from 1,000 to 1,500 in 6 years. And then I'm going to ignore everything else in the problem because this is what I need to figure out my rate, right? I have this 1,000 is my P naught, my initial population, and I know this 1,500 is the population after 6 years. And then of course T is equal to 6. There's 4 things in this equation and I know 3 of them. So if I take this P of T equals P naught e to the RT. P of T I can say is P of 6 in this case is 1,500 is equal to P naught, which is 1,000, multiplied by e to the R times that T, which is 6. I know everything in there except that R, and so all I have to do is figure out this R. So I'll start by dividing each side by 1,000 in order to isolate my exponential. This leaves me with 1.5 is equal to e to the r times 6 or e to the 6r. Right? Same thing. But I can rewrite this as a logarithm. It's a base e over here, so I'm going to write it as a natural log. So I have the natural log of 1.5 is equal to 6r. And I can then just isolate the r by dividing by 6. So whatever the natural log of 1.5 divided by 6 is, so here I get r is approximately 0.0676. And you'll want to use as many decimals as you can because the shorter this gets when you throw it into an exponential, the larger your error is going to be. So try not to cut them off too soon. I would use at least 3 non-zero digits. That'll help you get at least some level of accuracy here. But then the follow-up question in this one says, find when this population will reach 10,000, right? So I know this, I did the math to figure this out. Now I want to know, when is this thing going to get to 10,000? So that is to say, in my P of t equals P naught e to the RT, I want to figure out time. I want the P of t, whatever time that is, to be 10,000. I know my population initially was 1,000. E to the R I know, because I just figured it out. And now I want to figure out what t is. But t is also in the exponent of this, of the e, so it's kind of the same deal. I'm going to go through, divide each side by 1,000. That gives me 10 on the left, e to the 0.0676t, and then I just rewrite this as a natural log. So the natural log of 10 equals the 0.0676t. I want to isolate for the t, so I divide each side by 0.0676. And I've isolated my t on the right hand side, so it's t equals, and then the natural log of 10 over 0.0676. And whatever that is. So I'll take in the calculator and put in natural log of 10, then divide that by 0.0676. When I do, I get something in the neighborhood of 34 years. So after 34 years, this population of bacteria, whatever it is, probably not bacteria since we're talking about years, but whatever it is, it takes 34 years for that population to get to 10,000. Okay. And then the next concept that we'll talk about here, the next example, is radioactive decay. So if you have a radioactive element, plutonium, radium, things like that, francium, they decay. They start as a very large molecule, a whole bunch of very large molecules, but bits of it fly off or break off or they lose energy, and they physically change into a different element. And it happens, that's what radiation is. It happens like clockwork, if you'll allow me that pun, because a lot of clocks now use cesium radioactive decay to measure time. But the point here is that it does it very much in line with an exponential decay, right? And therefore we can say that we have an exponential function that describes it, and it looks strikingly similar to the population, right? But here we use A for the amount. The amount of radioactive material as a function of time is the amount A naught that we started with times e to the RT. The only real difference here is that my R is going to be negative in a decay, and it'll be positive in a population growth. Right? So let's take a look at little thing they call half-life. So if you have so much uranium, the half-life tells you how long in years typically before half of that gets decayed away, right? So if I start with 100 pounds of it, after however many years that half-life is, now I have 50. But it's going to take that exact same amount of time, and exact, I don't want to use the word exact, but it'll take that same amount of time for the 50 pounds that I have left to decay to 25. And then another time period to decay down to 12 and a half, and so on, right? And so, let's say that we have some uranium. In this case, we have uranium-235. And it has a half-life of 703.8 million years. Okay. Now there's two things that I can do with this. Since they gave me million years, I can actually write this as millions. So that would be 703.8000000, right? I can actually use this number in my calculations, or I can just take 703.8 and just note that my time period is scaled in the millions of years. And that's what I'm going to do here, rather than having to type in that pretty big ugly number. I'm just going to scale this problem in the millions of years, right? So if it has a half-life of 703.8 million years, I want to find R, right? And I want to find R, again, based on that 703.8 million years. So, that is to say, this equation, since we're talking about a half-life, the amount that I have after this 703.8 is half of what I started with. So I can write that as 1/2 of the initial amount. That's equal to the initial amount multiplied by e to the RT, and you can see here why it doesn't matter how much we have, because mathematically if I divide both sides by A0, it disappears. So divide by A0, divide by A0, and my equation simplifies down to 1/2 equals e to the RT. Okay. But I know this t happens to be 703.8 million years, so I'm going to write that in there as 703.8, and again my R then scales it into the millions. Okay. But I take this, let me go ahead and erase what I've got so I can finish this and solve for R. If I rewrite this as a logarithm, that becomes the natural log of 1/2 equals 703.8 times R. And this natural log of 1/2 appears a lot. It ends up being, I think, negative 0.693. I can remember it to 3 decimals, that's all. And then I can solve by dividing each side by 703.8. Right. And then my R, again scaled for millions, is then negative 0.0009849. And you can see, if I had used 703,800,000 instead, I would just get a whole bunch of more zeros in here, but it would still be the 9849 at the end, right? Okay. So, that's to find R, which I'll write over here. R is negative 0.0009849. Sorry, that's kind of small and in the corner there. But the next question says, using this rate, find the amount of time that has passed after a sample of 1,000 kilograms to decay 250 kilograms. Okay. So that is to say that my amount that I have after however much time has gone by is 250. So in this equation, the amount after some time is 250. The initial amount here is 1,000. R, I know, is negative 0.000989. And then that gets multiplied by t. So I need to pull this t out of the exponent. So I'll divide each side by 1,000. This gives me 0.25 on the left, or 1/4 if you will, is equal to e to the negative 0.000989 t. Rewriting this as a log gives me the natural log of 0.25 equals negative 0.000989 t. And then I want to isolate the t, so I'll divide each side by negative 0.000989. Oops, not a log. Okay. And if I throw this into the calculator, the natural log is 0.25, and then I divide that by negative 0.000989, I get 1407.5-ish, right? Rounded to the nearest decimal. But again, because R is compensating for the fact that this T was given to us in millions of years, then this is in millions of years as well. Right? So then it takes, in fact, since it's 1,407, that's a trillion years. 1.4 trillion years. I'm sorry, billion. Forgot where I am. Billion years. Alright, let's do one more. Carbon is often used to date an object. We have a pretty good idea through time periods, the carbon-14 levels or carbon-12 levels in the atmosphere and in objects. And so I have the half-life of carbon-14. And a lot of times you'll see this with a little lambda, a Greek letter for like the L, with a little 1/2 down here, but that's the half-life. The half-life of carbon-14 is 5,700 and something years, 5,730 years. Which is to say, the amount after time equals A naught e to the RT can be turned into 1/2 the initial amount is equal to that initial amount, e to the RT. And once again, that A naught just cancels out whenever you play with the half-life. Because that's half the initial amount, you would divide that over and just get a half anyway. So I get 1/2 equals e to the R, which I am looking for, and t, which is 5,730. So I rewrite this as a natural log. The natural log of 1/2 is equal to R times 5730, and then divide each side by 5730. And then my R is completely isolated. I have the natural log of 1/2, which is negative 0.693 something. Divide that by 5,730. And I end up with R as being about negative 0.000121. And that's my decay rate for carbon-14. So if we use this, R is negative 0.000121. Then an archaeologist claims to have found an object used by Jesus. An examination of the artifact shows that it contains 87% of its original carbon-14. So we want to estimate how old it is, and carbon dating is not going to give you the date and the time that something was made or buried or whatnot, but it will tell us within plus or minus enough years, usually, that we can say, yeah, that's probably wrong. Or, hey, that might be right. Right? So we're claiming to have something used by Jesus. It's telling us to use 2,000 years-ish. We're going to estimate anyway, so what's another 20 whatever, or negative 10 years, depending on who cares. What we want to do here is the amount of the carbon, the amount at a function of T is equal to A naught e to the R, which is the R for carbon-14, negative 0.000121 times T. And we're trying to figure out what that T is. I know I have 87% of my initial carbon. And so this is the A of T. And that's equal to A naught e to that number, negative 0.000121 T. The A naughts cancel out, and I end up with just 0.87 equals e to the negative 0.000121 T. Rewrite this as a log, I get a natural log of 0.87 is equal to negative 0.000121 T, and then divide negative 0.000121. When I do that natural log divided by that number here, I've isolated my T on the right hand side, so I get T is approximately 11 to 51. So it's old, but it's not old enough to substantiate his claim, right? And so we would say, no, you didn't find the Holy Grail, keep looking, or do whatever. But that's that. So, all right, thank you guys, and this is the last one for this course. So I hope you've enjoyed it, and take care of yourselves.